solve few important questions on potential energy, electrostatic potential energy. So starting with the first one, the work done by external agent if Q naught is taken from A to B. Okay, in these two examples, charge Q naught is taken from A to B, from A to B. So we have to find the work done. Okay, again to calculate work done, we just need to find initial potential energy and final potential energy and their difference. Okay, so let's say if charge Q naught is here and it is moved from here to here, there will be three pairs. One will not be disturbed. The distance between these, as it is perpendicular bisector, so the distance between these two is nothing but L square plus X square root, and this distance will also be same. So the pair between Q1 and Q naught will have same energy whether Q naught is here or here, and also the pair between Q2 and Q naught will have same energy whether Q naught is here or here. So I can say that there is no change in potential energy. U initial is equal to U final. Yeah, for calculation purpose we can always write K Q1 Q2 by 2L plus K Q naught Q1 by root of L square plus X square plus K Q naught Q2 by root of L square plus X square. But the change or the work done will be 0. In this case, point charge Q naught is taken from A to B. Okay, again this pair remains same, Q1 and Q2. The distance between Q2 and Q naught was L and final distance is also L. So the only pair that is changing is Q1 Q naught. So we can say delta U is U final minus initial. Instead of writing potential energy for the whole system, I will write potential energy of only for that pair which is changing. Okay, so this is the pair which is changing in its potential energy. So final is the separation between Q1 and Q naught will become 3L. So K Q1 Q naught by 3L, this is the final potential energy, and minus the initial potential energy between this pair is this. So by solving this, I can get K Q1 Q naught by 3L multiplied by minus 2. Okay, so minus 2 K Q1 Q naught by 3L is the amount of work done. What is the work done in the next question? What is the work done if dimension is doubled? If the dimension of this is doubled, again we can say the initial potential energy will be 3 kq square by L. So final potential energy when L is replaced by or A is replaced by 2A, it will be 3 kq square by 2A, and change delta U final minus initial will obviously be minus 3 by 2 kq square by A. In this initial potential energy, I have just solved this question in the previous video. Initial is 0, and if we double the distance, again final potential energy will be 0, and work done or delta U change in potential energy will be 0 in this case, because the potential energy of the system is itself 0. By doubling the distance it will remain 0, so 0 minus 0 will give you simply 0. A charge Q and mass m is thrown towards an identical charge with speed v. Find the minimum separation, and we can assume there can be two parts. First, that charge Q is fixed. One of the charge is fixed. One of the charge is fixed. Okay, so I am solving for this assumption, and we can always assume that both are free. Okay, so that will be slightly different. For I'm solving for this, one of the charge is fixed. Okay, so let's say this is the fixed charge, this is fixed. and we throw a charge with speed v towards it from a very large distance. Okay, this was infinite. When it reaches to this point, let's say this is the minimum distance, d min, after that it will stop. Okay, so at this point velocity will be 0. We can say the charge has lost all its kinetic energy. So where this kinetic energy has gone? This kinetic energy must have gone to potential energy. So I can write loss in Ke is nothing but gain in Pe. How much loss? This much, half mv square minus 0, because the final energy is 0. It has stopped. Only then the distance will be minimum. If it will move further, the distance will no more be d minimum. So half mv square minus 0 is this, and gain in potential energy will be simply u final minus u initial. Final is kq square, as the charges are identical, and d min minus 0, as the initial separation was infinite. Okay, so we can always get d min is equal to kq square into 2 by mv square. So that is the minimum separation between these two charges. Okay, so now let's solve the next part. If both the charges are free. Okay, if both are free, so what will happen? I have to draw two diagrams. One is, this is at rest, though it is free, but initially it is at rest, and it has thrown from a very large distance with a speed v. Okay, so what will happen at minimum separation? At minimum separation, they both must be moving with same velocity. This is a concept of kinematics, that at minimum separation the velocity along the line joining them must be same. So let's say that velocity is v dash. Okay, both have same mass. So applying conservation of momentum, I can say mv plus 0, the 0 for this, is equal to mv dash plus mv dash. Using that, we can always calculate v dash as v by 2. Okay, again it has come to this point, it has gained potential energy, because the initial potential energy was 0 and final potential energy is not 0. Okay, let's give this symbol r min. Okay, so what will happen? There will be again loss in Ke, and there will be gain in Pe. So how much loss? Loss is always initial minus final. So initial is half mv square plus 0, 0 for the charge which is at rest, minus initial which is final, half m into v dash square into 2, because there are two charges which are moving with v dash velocity, both have same mass. So gain will be u final minus initial. Final is kq square by r min, and there was no initial potential energy as the separation was infinite. Solving this, just put the value of v dash here. It will be half, it will be 2 cancel, 1 by 4. So half minus 1 by 4 will be 1 by 4 mv square as kq square by r min. We can find r min as kq square 4 by this mv square. Okay, so this is the minimum separation when both are free. Okay, so resolve these questions and enjoy.